Hello and welcome back to TechTangents. I'm Rowan and I'm here with Pranav.
Hello, and nice to be back. If you remember last time, for our first episode, we looked at mathematical applications in cryptography.
If you haven't already had a look at that, make sure you do after listening to this episode. And today in episode 2, we're going to talk about optimization algorithms.
Specifically, the powering systems at Uber, Amazon, airlines, and more. By optimization algorithms, you mean the maths that figures out the best solution, like the fastest routes, cheapest schedules, or best matches, given all the constraints, right?
Yeah, exactly. So every day we take, say, a taxi from Uber, shop on Amazon, or fly with an airline, and behind the scenes there's incredible algorithmic work going on. Uber has to, say, match riders and drivers to minimize waiting time.
Amazon needs to decide which trucks go where. To cut fuel and delays, airlines must pair up crews and planes flights under strict rules.
All of that is optimization. We choose an objective like minimize distance or wait time and obey constraints like traffic, time windows, crew rest rules, etc. So in this episode, we're going to dive deep into how those algorithms work from theory to practice,
Hold on.
step by step.
Let's not give away too much just yet. First up, graph algorithms. Graph theory is everywhere in these systems. How does it connect?
So a graph is a mathematical model. It's got points and links, nodes and edges. Think of a city map. Intersections are nodes, roads are edges, with lengths or travel times as weights. That's a weighted graph, exactly what we have for routing. In general, graphs let us model networks of roads, routes, or even relationships.
One classic problem in the shortest path problem. Given a graph and a starting point, what is the path of least cost meaning distance, time, etc., to reach another node on the graph? This is fundamental to navigation. A famous algorithm for this is pronunciation, Dijkstra algorithm, conceived by Edgar Dijkstra in 1956. In a nutshell, Dijkstra algorithm finds the shortest path from a source node to all other nodes in a weighted graph. For example, if our nodes are cities and edges are road distances, it will compute the least distance route from one city to every other. Let's start with something familiar, shortest path algorithms. You've used Google Maps, yeah?
Yeah, obviously. And what's cool about Google Maps is when you ask for the fastest route, your phone's quietly running something like Dijkstra's algorithm behind the scenes.
Yeah, it's a classic. Invented in the 1950s by, once again, Edgar Dijkstra. The idea is built on graph theory. Think of roads as a graph, where nodes are places like junctions or cities, and edges are roads, each with weight like time, distance, or traffic delay.
So now here's how it works step by step. Imagine you're starting at a city, you mark that as your current location, and then you label the distance to it as 0 because you're already there. Every other city starts off with a distance of infinity because you don't know it so far.
Then you look at all the neighbouring cities you can go to from where you are. For each one, you calculate how far it is if you were to go through your current city. If that distance is shorter than what you had written down before, you update it.
Yeah, so once you've checked with all your neighbours, you mark your current city as visited, you've done it, and then you pick the unvisited city with the smallest distance next and you repeat that process.
Ah, right. It's a bit like choosing the cheapest airline ticket available at every step, building your route outward and never going back. You're expanding outwards in rings, always choosing the cheapest option so far.
Yeah, and the best bit about it, it guarantees the shortest path as long as your weights are non-negative. That's perfect for things like travel times with uses in like Google Maps and other navigation apps. But wow, that sounded quite complicated. Pranav, how about you try and explain it as if I'm a 5-year-old for a bit of a simpler version?
I'm not AI, but alright, if you say so. Right, and for the explain like a 5-year-old version, imagine you're at a playground with paths connecting all the swings, slides, and seesaws. You want to find the shortest way to the ice cream one.
Yeah, so would you say like start by seeing how far each path goes from where you are? If one's 3 steps and another's 5, you're going to remember that. And then from those next spots, you're going to keep checking what's the shortest way to go forward. You're always taking the easiest steps first.
Yeah, you just want the ice cream fast, don't you? Eventually, you'll find the quickest way to the ice cream without ever trying every possible path. Once again, Dijkstra's algorithm.
Hopefully you don't need to say that one again.
Hopefully.
Now, say scale that up, Google Maps is doing this across millions of junctions with live traffic data. Amazon's doing something even harder. They're not just solving this problem once for one user, but thousands of times per second for every delivery van with hundreds of parcels.
And that's why we use variants of, once again, Dijkstra's algorithm too, like A-star, which adds an educated guess called heuristic to estimate how far you still have to go. This makes it even faster, especially on massive maps.
So whether you're finding your way to a concert or a robot's navigating a warehouse, it's all Dijkstra's legacy. All his algorithms are working. I ordered something on Amazon yesterday. It's going to get here tomorrow because of Dijkstra.
Wow. Now that we've covered graph-based optimization, like shortest path matching, let's move on to different class, linear and integer programming, which power scheduling and allocation problems. I know linear programming is huge in optimization. Can you explain what it is and how it's used?
Well, I'm not AI, but sure. Linear programming, also called linear optimization, deals with problems where both the objective and all constraints are linear functions of the decision variables. Formally, we want to maximize or minimize a linear object, like c to the power tx, subject to linear inequalities such as ax is less than or equal to b, or maybe ax equals b, and possibly bounds like x is greater than or equal to 0. For example, an airline might want to minimize total crew cost. Objective equals cost per pairing times by x, subject to constraints that every flight is covered by exactly one crew pairing. Here each variable, x, I for example, is binary. 1 is pairing, I is chosen, 0 otherwise, and the constraints are linear. For example, the sum of all the x's over all the pairings covering the flight equals 1.
That makes sense. And building on that, wait, I'm too lazy to say linear programming, I'm just going to say LP. And building on that, in LP problems, the set of feasible solutions forms a convex polytype, a shape in space defined by the intersection of half spaces. Convexity is key. What is convexity?
Key.
Good. Any line segment between two feasible points stays feasible. Think of it like a constant. It stays what?
Feasible.
Good. It stays feasible. Because both objective and constraints are linear. LP is a convex optimization problem. Convex, we know about convex and concave, right? Do we?
Of course.
Concave, think about you're in a cave, so it's an upside down curve. And think of convex as the opposite, as a smiley face, or a curve facing upwards. This means any local optimum is global, and powerful algorithms like the simplex method or interior point methods can find optimum reliably and efficiently for large problems. In fact, linear programming is the backbone of many optimization systems. If you see straight lines and equations, it's what?
Linear programming.
Or as I like to call it, LP.
Exactly, and a nice illustration comes from OR Tools. That's Google's open source optimization library. That has a toy LP, linear programming. So for example, if you want to maximize 3x plus 4y, you do that subject to x plus 2y less than or equal to 14, 3x minus y greater than or equal to 0, or x minus y less than or equal to 2. Here the objective and constraints are all linear expressions. The feasible region is a convex polygon, a triangle, and the simplex algorithm would move along vertices of that polygon to find the maximum objective. Now, do you think variables can be integers too?
Good point, and yes, they can. The pure LP, linear programming we solve, has real variables, but in real problems, variables must be integers or binary. Well, in most problems. That's mixed integer linear programming, or I'll call it MILP. For example, crew scheduling has integer, often binary decisions. Include this flight for the crew or not? MILPs, or for you guys to understand, mixed integer linear programming are NP hard in general, but solvers tackle them via branch and bound, cutting planes, and heuristics. Often we say we use LP or MILP to be more specific to model scheduling or assignment problems. Speaking of which, how do we actually solve an LP or MILP in practice?
That's a great question. In practice, we typically use solver libraries. The steps for coding an LP are, well, first of all, you want to declare the solver, such as OR tools, MP solver with GLOP, GLOP, or skip, SCIP backends. Then you want to define the variables, and then you're going to add the linear constraints. Then you want to set the objective, and finally you want to call the solver and retrieve the solution. Google's OR tools example lists exactly those steps.
Right, and as you mentioned earlier, because LP is convex, the optimum always occurs at vertex of the feasible polytype. Algorithms like simplex exploit this by walking from vertex to better vertex until no improvement is possible. It's like constant improvement. Think of it that way. Interior point methods take a different approach, moving through the interior. For large-scale LPs, linear programming's state-of-art solvers like the IBM's Cplex or Gorobi can solve them quite quickly. Practitioners rely on these or open tools like CoinOR or OR tools.
Yeah, exactly. And to make this more concrete, airline crew scheduling is a classic LP/MILP use case.
Yes, the industry splits it into two phases, pairing and rostering. In the crew pairing phase, we group sequences of flights into legal pairings. Each pairing has a cost, and the global is to cover all flights at minimum cost. This is modeled as a set partitioning integer program. Because there are thousands of flights and pairings, these LPs are enormous. Yet airlines save 5 to 10% of crew costs with a good optimization, which adds up to around millions of dollars.
Yeah, that's a lot. And in the second phase, crew rostering, you assign actual crew members to those pairings while respecting work rules and preferences. This can be an LP or an MILP problem, or it can also be tackled with heuristics as well. It's hugely complex scheduling puzzles involving regulations like rest periods, skill qualifications, and maximum work hours. OR tools and commercial solvers like Cplex massively help here.
Another big example would be vehicle routings for deliveries like Amazon's. The one you got yesterday or today?
It's arriving tomorrow. I ordered it yesterday.
All right.
Yeah, exactly. And you can model it as a TSP or VRP with constraints like vehicle capacity and time windows. You then set up an ILP with binary variables, and if a truck goes from customer I to customer J, then you know something's happened. The objective is to minimize total distance, subject to flow constraints. Though the resulting ILP is NP hard, solvers and heuristics handle moderate cases well.
And for factory scheduling, if tasks and times are divisible nicely, you could even do it with pure LP. But more realistically, complex scheduling like job shop scheduling needs constraint programming or MILP. What does MILP stand for?
Oh, is it multi-integer linear programming?
Nope. It's mixed integer linear programming. Did you guys remember? OR tools even has factory job shops examples.
Yeah, exactly. And large operations such as factories or airlines, like we've mentioned, rely on these tools for employee shift planning and job shop scheduling.
So companies use libraries like OR tools or commercial solvers, turning real-world problems into LP formulations.
Right. Modeling is the hard part. Solvers handle the computation. Cplex, Go-By, Skip, and OR tools, GLOP, CPAT, STAT. That's a lot of abbreviations, but we haven't mentioned all of them before. They all solve everything from routing to scheduling efficiently.
Speaking of hard problems, earlier you mentioned that some are NP hard, like TSP and VRP. What happens when LP, or in my case, MILP, gets too slow?
So then the companies often turn to heuristics and meta-heuristics. Those are faster but approximate methods. For example, the travelling salesman problem, TSP, that's a hallmark NP-hard case. Heuristics come in many forms. So, for example, greedy methods like the nearest neighbour, fast but sometimes far from optimal. Local search methods like 2-opt or 3-opt, tweaking solutions to improve them. Or meta-heuristics like simulated annealing, taboo search, genetic algorithms. They're all designed to avoid getting stuck in bad local minima.
Wait, does that include the ice cream problem? Oh wait, maybe not. Okay, interesting. And even though heuristics aren't perfect, they get incredibly close to optimal for large problems, although they can take a bit of time. Like only 2 to 3% off for million node TSPs?
Yeah, exactly. In practice, companies often use hybrids, heuristics to narrow down the search, and then LP or MILP to polish the best options. What does MILP stand for?
Mixed integer linear programming.
Oh, getting better, are you? Like airlines, using heuristic pairing generation to combine with LP optimization, or Uber using heuristics for real-time driver-rider matching.
That brings us to tools. We've mentioned OR tools, Cplex tools, Gurobi tools, and what do companies actually use? There's a broad set. Google OR tools, open source with LP and MILP, routing, scheduling solvers. Moreover, we have IBM iLog Cplex, a commercial powerhouse, popular in airlines for LP/MILP. Gurobi, another top commercial solver known for speed and ease of use. CSIP and CoinOR, or as some people call it, CBC. Open source options, specialized systems too. Amazon's Condor optimizes package routing by smartly shrinking route options. Isn't that smart?
That is pretty smart.
And for scheduling specifically, constraint programming tools come in, right?
Yeah, exactly. OR Tools CP SAT solver is heavily used for shift and job shop scheduling. I always get that mixed up. Other options include OptiPlanner for timetabling and mustering, and commercial products like SAS scheduling. Constraint programming helps express rules like, for example, no back-to-back shifts, which are common in real operations.
So in real companies like airlines, do they just buy off the shelf software?
Not quite. Airlines often build bespoke systems that integrate optimizers into their IT infrastructure. They pull flight schedules, crew databases, and run optimizers continuously or nightly, and they often save millions by optimizing crew utilization and reducing inefficiencies.
And on the delivery side, Amazon, FedEx, UPS, they all implement custom optimizations to batch and reroute more efficiently. It's fascinating.
It really is. So let's recap some of the key points, because it's been quite a complicated episode.
Quite a complicated one.
So we've looked at graphs and the shortest path. They're foundational for routing. So for example, they're used by people like Uber. We then looked at linear programming. That's the backbone of crew scheduling, resource allocation, and routing. Then we moved on to heuristics. That's essential for NP hard problems like TSP, the traveling salesman, and VRP. Tools. We then finally looked at tools, libraries like OR tools, Cplex, Gurobi. You're probably tired of hearing those by now. We also looked at custom-built engines like Amazon's Condor system. Advanced optimization engines directly save companies time and money. Uber saved tens of years of wait time daily, and airlines save millions annually.
Speaking of getting tired of listening to something, what does MILP stand for?
Oh, multi-integer linear programming.
Come on, it's not. That's wrong.
I'll get it next time.
Better get it next time. Did you guys get it?
We'll test you next episode.
It was mixed integer linear programming. Be ready for the quiz. Anyway, we hope this has demystified the complex math behind everyday conveniences. For students, developers, engineers out there, understanding these underpinning can inspire you to tackle your own optimization puzzles. Thanks for tuning into TechTangents. Keep exploring, keep questioning. Make sure to like, subscribe, comment, share, follow. Listen to all our podcasts, and we'll see you in the next episode.
Goodbye.
Goodbye.